Alrighty, here's question number 3. We're given that y sub 1 of t, which is equal to e to the negative t, and y sub 2, which is equal to e to the 2t, are solutions of this ODE here. So y double prime minus y prime minus 2y is equal to 0. We're going to determine if y sub 1 and y sub 2 are linearly independent or not. Okay, and then if they are, then we're going to form a general solution. So there are two ways to determine linear independence, and I'll show you both of them here. Okay, so the first way is to see if they're constant multiples of each other or not. Okay, so this is the constant multiple method, I guess you could call it. That's a very unofficial term. So constant multiple method. Okay, so that just means when we set up some equation like this, so when we have e to the negative t, so here's our y sub 1, is equal to e to the 2t, which is y sub 2, then we just stick a constant in front of one of them and see if this actually makes sense or not, okay? So if we were to, let's say, multiply by e to the t on both sides, e to the t, then these ones cancel out, and we get a constant should be equal to e to the, and we just add the exponents, so this would be a 3t, and this is not true, okay? This equation, so this is this function here, so we can say not true for varying values of t. Alright, so if t changes, by the way, we're like, let's say hypothetically or something, so let's say t is 0, then we get this right side is equal to 1, so c could equal 1, but then if t changes, then the whole value on the right changes, and that means that would contradict the whole left side being a constant, right? So this means that our functions, so we could say our functions, y sub 1 and y sub 2 are not constant multiples of each other, meaning that you can't just multiply by a constant to get the other function, right? So they're not constant multiples of each other, so they must be linearly independent. I'll abbreviate LI, linearly independent. Okay, so that's one way we could determine that they're linearly independent, and I'll show you the next way on the next slide. And then, of course, the other method is called the Wronskian, by taking the Wronskian. So I'll just say it's the Wronskian method. Okay, so this one, conversely, is by saying, so we have our y sub 1 of t, which is equal to e to the negative t, and our y sub 2 of t, which is equal to e to the 2t, the positive 2t. Okay, so to take the Wronskian, we just see if our answer is equal to 0 or not, okay? And the Wronskian is equal to the determinant when we set up our function. So this would be e to the negative t, and this would be e to the 2t. So we just stick our functions there. Then we take the first derivative of each of them, okay, and place them down here. So we have something like that, okay? So then when we actually take the cross, well, not the cross product, but the determinant of this, we take the product of this, so that would be 2e to the t, right? And then minus, we subtract the product of the other, so that would be minus a minus e to the t, okay? So these negatives actually turn positive, and our answer is going to be 3e to the t, okay? So this is the Wronskian of our two functions. The Wronskian is equal to 3e to the t, which is never actually equal to 0, so that means, so since the Wronskian is not equal to 0, this means that our original functions, y sub 1 and y sub 2, must be linearly independent of each other. Okay, so again, using a different method, we arrived at the same conclusion. Okay, so now, building off of that, we just have, so since they are linearly independent and they happen to be both solutions to our ODE, our original ODE, so since, well, let me continue this on the next slide where we have more room, okay? So we have y sub 1 of t is equal to e to the negative t, and then y sub 2 of t is equal to e to the positive 2t. So since we have that y sub 1 and y sub 2 are linearly independent solutions of the ODE, which is y double prime minus y prime minus 2y is equal to 0. Okay, that was just the given ODE, which we didn't really have to deal with in this problem here. But since they are linearly independent solutions, then we can form a fundamental set of solutions with them, which would be something like this. We could also write it with the explicit formulas, right? So this would be like e to the negative t, and e to the 2t, which means we can form our general solution, which is denoted by y of t, by taking a linear combination of our entries in our set, okay? So that would mean by saying like c sub 1, e to the negative t, plus c sub 2, e to the 2t. And that right here is our general solution. This composes all of the possible solutions to this ODE here, okay? Alrighty, so that's it for our practice problems video for section 4.1 on second order ODEs. I hope that helps, and good luck on your homework.